Dan is an assistant research professor of climatology with the Desert Research Institute and regional climatologist for the Western Regional Climate Center. His work is focused on drought research and applications for natural resource management, and his presentation today will focus on EDDI, EDDI, the Evaporative Demand Drought Index. And it looks like, Dan, we see your title slide, so I'll turn it over to you.
All right, well, thank you very much. Thank you for the introduction, and I also just thank you for having me today on the webinar. I really appreciate being able to share this with the group. I'm going to be talking about EDDI, the Evaporative Demand Drought Index. This is a tool that's been in development for several years, and it's gained quite a bit of traction with the drought monitoring community, but we're really just starting to introduce this to the fire community as we're seeing some potential uses for it there. And so this is a great opportunity just to get the word out there and hopefully spur some ideas on potential applications for this in fire management. So what I'm going to do is basically give you guys a background on EDDI and what it is, and then talk about the work that we've done related to wildland fire management. Before I begin, though, I do want to mention that what I'm presenting today, this is a result of a much larger effort. As I mentioned, it's been underway for several years. Our main collaborators are in Boulder. Mike Hobbins is leading that effort there. We're in the process of transitioning EDDI from an experimental product to an official NOAA operational product, and that transition should be complete by next summer, and so we're almost to that point. But I do want to acknowledge the large group working on this project. So the whole basis for EDDI and the presentation today is on evaporative demand. And the first thing I really want to do is get the group familiar on what that is and kind of how it relates in general to fire. And so evaporative demand, the simplest definition is the evapotranspiration rate that could occur given an unlimited water supply. And so evapotranspiration, or ET, that's the actual flux of vapor coming off of the surface vegetation and the land surface. And so evaporative demand are the atmospheric variables that are controlling how much could occur given a well-watered surface. And so this term evaporative demand falls under an umbrella of a number of different terms, including potential evapotranspiration, or PET, which is probably most familiar to most people, atmospheric demand, or reference evapotranspiration, and that type of evaporative demand that we use for EDDI. And so that cartoon there kind of depicts this reference radiation. And so there's a number of different ways you can estimate evaporative demand. A lot of those are temperature-based alone, but we strongly recommend that is. But it's pretty clear that these, but also fire weather, especially wind, humidity, are probably the two main that contribute to fire weather. A lot of people, it can often get confused between what's evaporative demand and what's actual evapotranspiration, as I mentioned before. And so the evaporative demand, again, this gives no direct information about the land surface. That is the actual evapotranspiration. And so with the evaporative demand, this has traditionally been used in the past for several decades to estimate the evapotranspiration from crops. So using the near surface weather, what you need to know from there is the crop type. And so if you know the specific crop type and the evaporative demand, then you can estimate what that actual ET is. Expensive to measure the actual ET, and so it's really popular to use a weather station and you can estimate the actual ET from there. So as I mentioned, traditionally it was used in agriculture, but over the past 10 to 15 years, there's been a much bigger push towards looking at evaporative demand in terms of demand that can lead to the moisture stress on the land surface. And so, you know, an example would be in the summer. And so we first started looking at this for agricultural drought. And so what you would see, you know, a drought doesn't just start, you know, overnight. It takes a little bit of time to develop. And so what you have is you start with sufficient moisture still on the surface, whether that's soil moisture or vegetation health. And then you can get this anomalously high evaporative demand, high temperatures, strong winds, low humidities, so the evaporative demand increases, and then this actually increases the ET at first, and then that reaches the tipping point where there's no more moisture left on the surface, and then you start to go into that drought. But the key is that the evaporative demand is often the first indicator to kind of signal that we can be going into this warning indicator of these kind of ag droughts or flash droughts, these droughts that develop kind of rapidly. And so then we started working on this evaporative demand in a simple, you know, the simple way to put it are these are normalized and so this is a map on the right showing a recent EDDI, a 1-month EDDI category. And so one of the main features about EDDI, and there's some other, and so the user can choose what time scale you want to look at, whether you want to look at short-term wetting and drying or long-term kind of extended hydrologic on the right hand. And so what that means is it's taking, ending at November 2nd and going backwards 1 month, taking that evaporative demand accumulation and seeing how that compares to all the other 1-month periods for that same time, going all the way back to 1980, and you can estimate the percentiles from there. You run it through a normalized distribution, and then you can estimate the anomalies. The North American Land Data Assimilation System version 2, or NLDAS. This is a combination of atmospheric and land surface model to get these variables. The variables we use comes out of land surface model. That's temperature, specific humidity, and everything south over the border at 12 kilometers spatial resolution. And again, it's updated daily. It does have about a 5-day lag right now, and so I pulled this map this morning. So if you go on today, you'll find the map available from about 5 days ago. They are the NLDAS group is working to kind of close that latency gap, so you can get something closer to real time, about 1 or 2 days. And so what this map really shows is the reds, you know, the oranges and the reds are above normal evaporative demand, and so that would be hot, some combination of hot, dry, windy, cloud-free conditions above normal evaporative demand. And then the blues would indicate a combination of cool, wet, less wind, and cloudy, and below normal evaporative demand. And this is kind of an interesting map for the last month. A lot of the center of the country is showing this below normal evaporative demand. A few hot spots of above normal evaporative demand are kind of central and northern California, which are still really going in their fire season because we haven't had kind of the big first big fall rain event yet. So that's interesting to note. And then in the southeast, there's a kind of another hot spot over Florida and some of the states down there in the south. And I also wanted to mention that so this has been kind of going on experimentally with the drought monitor community for several years. And about a year or two ago, the U.S. Drought Monitor, that's the map that's updated weekly, they adopted EDDI as one of their indicators, and so this is now incorporated into the weekly U.S. Drought Monitor maps. So I mentioned the timescales earlier, and this is really important for understanding how to use EDDI, kind of interpreting these different timescales. There's kind of two main categories, kind of the long-term and the short-term timescales. We kind of consider long-term anything greater than 3 months. That's kind of drought that has already emerged and has been persistent over time, or more of a hydrologic type drought. And so on the left, we have a 9-month EDDI, and so this is from this past summer, mid-July, July 15th, and so it considers the evaporative demand from the previous 9 months and how that relates to the climatology. And so what we can see there is this big bullseye of that ED4, which is the 98th to 100th percentile over the Four Corners region. And so this was showing unusually high evaporative demand over the past 9 months, and that really reflected the kind of the wet season and kind of the snowpack. They had a very dry winter and a low snowpack and a snow drought, and that was all really reflected in these longer time scale eddies. The other category are these short-term timescales. And I do want to highlight that we do compute EDDI all the way down to the 1 week time scale, so just looking at 1 week accumulations, which is almost getting down to the weather time scales. And as I'll show you later, these are the time scales that have seemed to show the most potential to being used by the fire community for looking at potential fire danger. And so then on the right we have the 1 month EDDI map, so it's the same ending date there, July 15th, but it's only considering the previous month's worth of evaporative demand. And I've highlighted a few regions, so this means like that drought may not necessarily have developed yet, but there is the potential for that given the high evaporative demand. And so we see that in the Northeast over New York, there's a very strong signal, but also over Northern California. And this was about a week before the Carr Fire began, and I have a little bit more on that later, but this could indicate increased drying of fuels or flash drying if you still have moisture left in those fuels. And the other thing I wanted to emphasize, and this gets to that point of why it's important to not use just a temperature-based evaporative demand if you have the data, to use a physically based model. And so Mike Hobbins, who's our main collaborator in Boulder, he's done some great work. He had a paper in 2016 that looked over CONUS and decomposed that evaporative demand equation into the 4 drivers of temperature, wind, humidity, and solar radiation using the sensitivity equations. And he was able to go month by month and look at which of the drivers which was actually contributing the most to the total evaporative demand. And so this is really important. And if you go across, we have January, February, March, we have all 12 months there listed. But if you look at kind of the summer months, June, July, August, September, even October, in the Southwest and other parts of the West, that's all showing red, meaning that wind speed is the dominant driver and contributing the most to the evaporative demand, and not temperature. And then other places like the Southeast, the downward shortwave radiation is the most important driver. And humidity in some cases is the most important driver. And the real take-home message is that EDDI is not always just going to be a reflection of the temperature anomalies, and it actually reflects more of the evaporative dynamics from some of these other drivers, which is I think can be really critical when understanding this for fire applications. So I want to spend some time on this. I put together just a little case study that kind of really illustrates this. So this was the 3-month EDDI for last summer, so ending at the end of August and covering the previous summer. And what we see here is a lot of blue over the Southwest, Southern Nevada, Southwest Utah, and Northwest Arizona. So that indicates well below normal evaporative demand. And so we can kind of look and see what was driving that evaporative demand. And so this map now is showing the same time period, June through August, but the temperature percentiles based on PRISM. And so if you look over that region, almost the whole region is in either one of these top two categories. There are some areas of red, which is the record warm going back to 1895, or this kind of orangish color, which is in the top 10%. So it was a very warm summer. So it doesn't appear to be that temperature was driving that low evaporative demand. And then I made these maps using Climate Engine, which I'll mention again later is another place to find EDDI. But you can get wind speed, you can get dew point, you can get solar radiation, drought indices, fire danger indices from Climate Engine. And so what I did is I looked over the same time period. I looked at the wind speed anomaly on the top left, the dew point anomaly on the top right, and then the solar radiation anomaly on the bottom left. And so what we see is that the wind speed was really below normal over that whole region. The dew point signal was mixed. There's a little bit of blue, which would be drier conditions, but a lot of kind of near normal, and orange, which is actually more moisture. And the solar radiation was also above normal, which would be less clouds. And so to me, without doing the full decomposition, this kind of shows that the wind speed was really driving the EDDI signal and not the temperature or the other drivers. So now that you guys have a little bit of background on the evaporative demand and EDDI and kind of how it might relate to fire, I want to get into our main project that we've been working on, rating EDDI and other drought indices mostly to fuel moisture. So we have a 2-year project that's funded by NOAA. It's a SARP project, which is the Sectoral Applications Research Program. It shows there it ends in 2018, but we actually got a 1-year extension on that project, so we'll be wrapping it up next summer. And we got that extension to spend a little bit more time with some of the stakeholders, which I'll talk about. And the main goal of this was to get more wildfire context into these NIDIS drought early warning systems. And so this map shows the different drought early warning systems. The California one started in 2010, and Nevada was kind of left out. There was just this hole on the map where Nevada wasn't part of any of these dues. And so I'm also part of the team that's developing, integrating Nevada into this dues network. And so we're really looking to see if we can, provide, can drought information provide any lead time on wildfire potential, and specifically how do the drought indices relate to fire danger indices, and mostly fuel moisture is what we looked at. And so the SARP grants, they have a really strong stakeholder component, and they really want you to get out there and interact with stakeholders and see how this project might lead to actual application of the research. And so our primary stakeholder that we've been working with is Predictive Services. We reached out to several different office groups in California and Nevada. We really only wound up with one real tester in North Ops in Northern California, Predictive Services. And we're looking to see if our research or data that we're working with can potentially maybe help improve these significant wildland fire potential outlooks and wildfire risk in general. And so, and I don't have to probably tell this group on the phone, but just in general, the drought-wildfire relationships are complex. And so the map on the bottom left there is the drought outlook from last winter, showing the spring. Then on the top is the March and April fire potential outlook. And there's definitely not a clear overlap where if there's drought or drought is expected to intensify, then there's definitely going to be fire there, or it's not the other way around, where if there's no drought, then there's definitely not going to be fire. In the southeast, there was drought, but the fire potential is below normal. And so these are very complex relationships, and it's not as straightforward as just saying where there's drought, there's going to be wildfire. And so we wanted to dig into that a little bit more. And so the main analysis that I did here was comparing different drought indices to fuel moistures. And the three that we looked at were the 1,000-hour, the 100-hour, and then the energy release component. And we compared those to EDDI and also 3 other drought indices, the SPEI, which uses precipitation and evaporative demand, the SPI, which only looks at precipitation, and then the PDSI, which looks at temperature and precipitation. And PDSI is a really older index from the 60s, but it's still really commonly used. And so this is just an example where we looked at how the seasonal fuel moistures compared to these drought indices at different time scales. And so I just want to focus kind of on the top row, which is the summer. And so what we did here was we took the June through August average 1,000-hour fuel moisture for every year going from 1979 to 2015. And we correlated that to these drought indices from the end of May. And so this would give us a sense if at the very beginning or very end of the spring, beginning of the summer, if you can get some sense of the fuel moisture by looking at what the drought conditions were showing. And so the best case scenario, what were EDDI and SPEI, they were pretty similar. EDDI actually performed a little better there. And so in some of these boundaries are the predictive service areas. And in some of these areas, you had EDDI and SPEI explaining greater than 60% of the summer fuel moisture variability. And so we think this could have some potential for looking at summer fuel moistures. Fall and winter, the correlations were much lower. There wasn't very strong relationships there. And then looking at spring fuel moisture, the relationships were pretty weak except for the kind of the southern areas there. And so kind of the take home from this was that EDDI and SPI show the most potential for predicting summer fuel moistures, which of course is the peak of the fire season. And so it was kind of neat to see that result. And aside from looking at kind of the seasonal scales, we also did a case study kind of looking at these shorter time scales and see how they might relate to fire danger in general. And so the case we looked at was the Tubbs Fire from last October in Sonoma County. And so this is just a map of the 2-week EDDI ending October 7th. The Tubbs Fire started on October 8th. The outline here is Sonoma County. Santa Rosa's kind of in the east central part of the county. And you can see, so this indicates that the 2 weeks leading up to the Tubbs Fire, the evaporative demand was very high in these top two kind of categories there. And so what we did, and Mike Hobbins provided the results for this, he did that decomposition that I was talking about, looking at the sensitivities, and we looked to see which variable was driving the evaporative demand during leading up to the Tubbs Fire. And so this first map, this first graph is showing that this is basically a moving sum of the 2-week evaporative demands. This would be like a 2-week EDDI in black. Anything above 0 is above normal, and then the dotted line are the percentiles to give some climatological perspective. And so two things really stand out here. Well, one is that the evaporative demand was above normal the entire time going back to early August leading up to the Tubbs Fire, and so this was persistent. And we saw two main peaks, one in early September, and then another one right as the Tubbs Fire was starting going into mid-October. And then we have October 8th there is the start of the Tubbs Fire. And so I'm going to overlay the next few graphs, the individual drivers, so you can see the contributions to the total evaporative demand. And so the first one is temperature. And so that's the red line. And just to be clear that this red line is the contribution to the total evaporative demand and not the actual temperature anomaly. And so what we see is that during this first peak here, that the red line was really above the black line, indicating a very strong dominance of temperature driving the evaporative demand during that first peak. But then something shifted, and that red line came down to near 0. And during the second evaporative demand peak leading up to the fire, there were really minimal contributions from temperature. Something else must have been driving these. If we look at the humidity now, the specific humidity, this is the blue line. It was below 0 during the first peak, indicating it was negatively contributing. So that would be actually more moisture or above normal humidity. But then as we shifted, we saw this kind of point again where the temperature started contributing positively, or humidity positively, and that became the dominant driver leading up to the Tubbs fire, which was really interesting because, of course, this fire was driven and spread by the high wind event, but it appears that the air mass had been drying out for days or even weeks leading up to that event. We also can look at the wind speed contribution, which is the green line. There isn't a huge contribution from wind speed, although there are some positive contributions. And we know this was a wind-driven event, so that could simply mean that wind in this region, the evaporative demand is not as sensitive to wind during this time of the year. And then finally, shortwave radiation also had some positive contributions. But the main take-home message here is that we saw this shift from temperature dominant to humidity dominant, a week or so, or even longer before the fire started. And so this can kind of trigger, kind of an increase in fire risk and potentially another tool along with fuel moistures and other things to kind of look at leading up to high fire danger events. And so, as I mentioned, we did have we wanted a bigger stakeholder involvement in this, but we did wind up with just North Ops Predictive Services actually testing EDDI. And so Brent Watcher was our main point of contact there, and he's provided some really kind of great initial feedback here on what he was seeing looking at EDDI during this past summer, and there were definitely some significant fires in Northern California. Most of this is fairly anecdotal, and we'd like to, we're probably going to do some interviews with Brent after the fall is over to get to drill down a bit more on this information. But this was from early June, right when he started looking at the EDDI, and so, he said he already had 2 cases from an event that yielded to 2,000 plus acre fires. And so he was looking at the shorter time scale EDDIs, the 1 week, briefing CAL FIRE, using this as a tool to brief CAL FIRE for potential for extra stress fuels and locations where those EDDI hotspots happened to be where those fires occurred. And this was interesting, relating kind of to fire behavior, where, talking about how there was 4 to 5 times the amount of fuel loading, and the fires were really active during breezy situations, no matter what the humidity was, even if there was 50% relative humidity. And so Brent was hoping to use EDDI to hone in on some of the more dangerous fuel conditions combined with stronger winds. And another kind of bit of feedback we got was around looking at the car fire. And so this map on the right is showing the 2-week EDDI from July 16th. And so that was about a week before the car fire started. And so leading up to that, there was definitely very high evaporative demand and a little hot spot of kind of the highest categories, right where the car fire started near Redding. And so what Brent was saying with this is that, it was a nice precursor towards determining the short-term drought and impacts on fuels as they dry and become more available for fire spread and growth. And this was interesting. I didn't really know how to interpret this. I don't know anything at all really about fire behavior, and so this, being on this call should be interesting for me to hear what some others have to say. But Brent was saying we're seeing D3 and 4 fire behavior, and then he says, saying this could be a stretch for purists because fire behavior is not just fuel alone. Basically, the drought monitor was showing much lower drought conditions, and he was seeing this kind of explosive growth in the fires where EDDI was kind of really high. And he actually said that he's probably going to recommend this to get into the NWCG Fire Behavior Fuel Reference Guide, which tells me that he finds it useful already after looking at it for one summer, which was promising. But we really need to look at this over a much larger area with more testers and just get some more eyes from other folks in other regions, seeing if they're seeing similar results. So we do have a full EDDI webpage where you can find the latest maps. You can get the archive maps going all the way back to 1980 every day. You can get time series And you can also access the data. This has links to the FTPs where you can actually access the archived maps and the data. So these are available. I think they're in ASCII raster format, so you can drag these grids into ArcGIS if you wanted to use them. We wanted to make this whole archive available for people for research or for using it kind of in real-time GIS type of applications. I also mentioned Climate Engine, and so we do have EDDI available on Climate Engine. It's the same as what we have on the NOAA page, but that is the NOAA pages are static maps. With Climate Engine, it's a Google Earth Engine interface or Google Maps interface, and it's run by Google Earth Engine. And you could zoom around wherever you want and zoom into these different regions. And so we also have the fuel moistures available there, climate variables, the full Landsat and MODIS archives to look at things like NDVI anomalies, all available on Climate Engine. So I encourage folks to check that out as well. I just wanted to summarize. So I kind of gave that overview of evaporative demand, and it's clear that the variables driving evaporative demand are key fire weather variables. EDDI was strongly related to fuel moisture at seasonal time scales, and there could be potential for adding value to monthly or seasonal outlook, especially considering that the seasonal forecasts from like dynamical models are really not very reliable, particularly in the summer. So some of the statistical information might add some more value. The initial testing by Brent was showing these shorter time scales are likely going to be the best for kind of the real-time monitoring related to the flash drying. Again, we need to really expand the testing, and we're thinking about expanding that analysis we did to CONUS if we can steer some more funding to do that. And then, of course, there's the question of how it might actually relate to fire behavior applications. And I also wanted to mention that we are developing seasonal forecasts of EDDI, and we do, I just thought of this now, and I didn't put the link in, but I can provide it if people are interested. We do have a link where we have EDDI forecasts from 1 to 6 months available, which could also help with some of this. And I think that was all I had. And I guess we'll see if I have time for a question or two, but if not, I can take them offline. Thank you.
All right. Thanks for that, Dan. That was really interesting, especially the relationship to some real fires that we saw this summer. I wondered if anyone has any questions. We have about 2 minutes, and you can raise your hand or type it in the questions panel.
So this is Morgan. We do have a couple questions in the panel, so I'll read the first one aloud. EDD timescales. Can the EDDI be calculated for a longer time period, such as a 5-year period, and would that be meaningful for fire managers?
Yes, it can. The main issue there is if you start calculating at the longer time scales, you lose part of the climatology since you're accumulating multiple years, and your distribution becomes smaller, which is fine, but it just reduces the kind of uncertainty in the distribution a bit. We've kind of looked at those longer time scales for things like precipitation, which are more useful for drought management. I really can't speak to if they would be useful for fire management or not. They would give you a perspective on long-term drought, though, really, and it can be computed. We only have it available out to 1 year, but it can be computed.
Okay, thanks. Next question, will Alaska be eventually included in future testing?
Great question, and I should have mentioned that there is a global EDDI product in development. Mike Hobbins is working on that, and if we do expand, we would love to have testers in Alaska as well. And I don't know who's all on the line from Alaska, but we are talking with a few folks up there that are interested in potentially testing up there.